Hi everyone, welcome back to Chem Help ASAP. Today we are going to be talking about spectroscopy and specifically the Beer-Lambert law, also known as Beer's law. Now, before we can really dive into Beer's law, we do need to do a quick review of waves and the electromagnetic spectrum. So let's get started. So first, let's discuss properties of waves. So waves have a wavelength. Now, this is the distance between two peaks or two troughs in a wave. So looking at my sample wave down at the bottom of the page, I could measure from one peak here to one peak here, and this distance would be the wavelength. I could also, of course, measure from a trough to a trough, and that would give me the same distance, which is the wavelength again. The amplitude of a wave is the magnitude of the wave's displacement, or half the height of the wave. On my sample wave, if I'm going to chop that wave in half, this would be the amplitude right here. Finally, we have frequency, and this is simply the number of waves, sometimes called cycles, that pass a specified point per second. Now, this is often measured in hertz, which is the same thing as 1/seconds or per seconds. This is not something that I can actually show on my picture because the wave would have to be moving. But you could imagine you're at the beach, you stand at a specific point, and how often waves hit you is the frequency. All right, so those are the properties of waves. Now let's talk about mathematical equations with waves. So there is a relationship between wavelength and frequency. It is given by this mathematical equation right here. C is your speed of light. Of course, just like we saw over here, wavelength is lambda and frequency is nu, just like we saw here. So if you know the wavelength, you can calculate the frequency and vice versa. They obviously have an inverse relationship. There's also a relationship between frequency and energy given by this equation right here, where the energy is equal to Planck's constant times the frequency, where again, h is a constant. It is a given number, just like the speed of light is a constant. Now, I can combine these two equations to give an equation with wavelength and energy given right here, where again, if you know the energy, you can calculate the wavelength and vice versa. And just to make this complete, I do want to show the constants down here. So your speed of light is 3 × 10⁸ meters per second. And Planck's constant is this long guy right here, and that is measured in joules times seconds. Again, just a very quick overview on the properties of waves and our mathematical relationships. Now let's review our electromagnetic spectrum. Okay, so you can see down here at the bottom, we've got wavelength and we have frequency. Again, you can see this is an inverse relationship. As my frequency decreases, my wavelength is increasing. So this just gives you an idea kind of where you are in the electromagnetic spectrum. Now, different parts of the electromagnetic spectrum will do different things to molecules. So if you're up here in X-ray territory, you are going to be breaking these bonds. So you can see this bond is breaking. You're also going to be doing some ionizing there as well. This is why X-rays are harmful and you want to limit your exposure to them. After X-ray territory, we move into ultraviolet territory, also called UV ray territory. And this is where you're going to have more electronic excitation. So you're going to have absorption and you're going to have emission. These are molecules that are literally absorbing the energy from these waves, and they are also emitting waves of their own. Now, this absorption emission range does include also the visible light range. Now, this is obviously just a teeny tiny portion of our whole electromagnetic spectrum, but our visible light does include this absorption and emission. After the visible range, we've got infrared. This is where you get vibrational energy, so molecules will vibrate in this region. And then, of course, you move to the microwave region, and this moves from vibrational energy to more rotational energy. While I do show distinctions between each of these regions, just know that there is actually a gradual transition. So not all molecules will move from vibrational energy to rotational energy right at a wavelength of 10⁻⁻�3. This is a continuum. So in reality, there are very gradual transitions between all of these different sections. So what do we want for our spectroscopy for Beer's law? We want to be in this ultraviolet and visible range. So oftentimes you will hear this called UV vis spectroscopy. We want to hit this electronic excitation where we're having absorption and emission of the molecule. So we definitely don't want to do any bond breaking. And for this type of spectroscopy, we're not interested in vibrational or rotational energy. Now remember, when we're talking about absorption and emission, we first have to define ground state. Your ground state is down here at the very bottom. It is going to be your lowest energy state. Any state that is above the ground state in energy is going to be an excited state. So all of these here are excited states. Now, as a reminder, when you have, say, absorption, you might be starting in the ground state and moving to an excited state, but you can also have absorption from one excited state to another excited state. And this is also true for emission. Very often you will emit back down to the ground state, but you do not have to. You can emit from one excited state to another excited state. And that is a very quick review of the electromagnetic spectrum. Now let's talk about how spectroscopy actually works. So this is just a schematic of a very general type of spectrophotometer. You are going to have a light source. Generally, you're going to have a monochromator. This is going to select your wavelength. So very often when you select a particular wavelength, we call that monochromatic light. And that just simply means that this light is one color. Because again, remember, we are working in the UV range a little bit, but a lot of this is in the visible range. So you choose one color. Once you have selected your wavelength, then you have an initial amount of irradiance that is coming out of this wavelength selector. Now, irradiance is energy per unit time per unit area. This is very often measured in watts per meter squared. You can also think of this as intensity or radiant power of light that is, again, coming out of this monochromator. It is going to hit the sample right here. Now, your sample is going to have a known path length, or the length across this sample right here. Very often these samples are measured in something called a cuvette, which has a very specific and very well-known path length. Commonly, these are 1 centimeter. Now, once the light has passed through this sample, the irradiance now has changed. So we call this value P instead of P naught. Again, you can think about this as the intensity has changed or the radiant power has changed because it has passed through the sample. And then finally, we're going to get to some kind of detector here, some kind of light detector, which will tell us what this irradiance actually is. Okay, so what do we do with these values P naught and P here? Well, we talk about the transmittance of the sample, or you can think of it as how much light is transmitted through the sample. This is something that makes sense to us, right? So your transmittance is going to be P over P naught. Again, this is the fraction of light that passes through the sample. You can see in my table here, I give values of P over P naught, and it's going to range from 0 all the way to 1. Now, what is even easier to talk about is actually percent transmittance. So percent transmittance, you can see I put in my second column of my table here. This is going to run from 0 to 100%. So you either get 0 transmittance or you get 100% transmittance. And obviously there is a direct relationship between all of these values. Now, I did not show actually 0 transmittance because if your sample has 0 transmittance, you have other problems that you have to deal with. Percent transmittance is great, but you can see I'm switching over here to absorbance. Why are we switching to absorbance? Well, absorbance is actually directly proportional to concentration, which is usually what we want to measure. So let's talk about how we take transmittance to absorbance. We're actually going to take the negative log of our value of transmittance, and that equals absorbance. Or you can think of it as log of P naught over P. Again, mathematically, these are the same. So use whichever explanation makes the most sense to you. Instead of transmittance, we can think of absorbance as, again, the fraction of original light that was absorbed by the sample instead of the fraction of light that passes through. Obviously, they are related. Your values for absorbance are going to run from 0 to 2. Now, ideally, you want absorbance to be about 1 if you can get there. But for most spectrophotometers, anywhere from 0.3 to 2 is okay. It does depend on what kind of spectrophotometer you have, which is why I think most people try to aim for that absorbance of about 1 for their sample. Okay, now we're finally going to actually talk about the Beer-Lambert law, again, sometimes just called Beer's law. So here it is mathematically. Absorbance equals molar absorptivity times path length times concentration. Okay, let's break this down just a little bit. This value epsilon here, this is the molar absorptivity. It is unique to each compound. So it is going to describe how much light is absorbed at a particular wavelength. So this is just at one wavelength by a particular compound. So again, each compound has a value of molar absorptivity, and that value can change depending on what wavelength you choose. So it's really important when you're doing Beer's law that you choose a compound where you know the molar absorptivity and you know it at whatever wavelength you are using on your spectrophotometer to measure it. Now, sometimes in older literature, this is called an extinction coefficient. They are the same thing. The units of molar absorptivity are usually 1 over molarity times centimeters, or sometimes it's written as molarity to the -1 times centimeters to the -1. This is going to make absorption unitless, which is what we want. Okay, so that is molar absorptivity. Let's talk about path length. We've talked about this a little bit. This is just the length of the sample. Again, it's usually placed in a cuvette of very well-known path length, and commonly that path length is 1 centimeter. Finally, C is concentration. This is a little easier to understand, and we usually measure this in molarity. Of course, you can measure concentration in a different unit, but you'll just have to make sure that your molar absorptivity unit, again, it's usually a molarity, but if you want to switch to molality, just make sure your molar absorptivity gives you units of molality here if you're going to use molality here. You just want to make sure that your units match. Going back to the mathematical form of Beer's law, obviously this is linear. Absorption is directly proportional to concentration. This is what makes it so useful. So when we plot absorbance versus concentration, we get a nice linear plot. Yes, there's always going to be some noise in your data, but notice it's going to go through the origin, because if you think about the formula for a line, y equals mx plus b, and Beer's law, you'll notice that for Beer's law, your B value is 0. So again, this is just a really quick and easy check as you're collecting data. Does your line that you're extrapolating go through the origin? It should be very, very close. Now, at this point, you might be saying, this is great, we're going to do a lab on Beer's law, but is this actually used in real life to do anything useful? And yes, actually it is. Because it's such a great tool for determining concentration, it's used for things like calculating oxygen saturation in tissues, or bilirubin in a blood sample, or even concentration of hemoglobin. So Beer's law does have very practical and very useful applications in the real world as well. All right, but if you're doing a lab on Beer's law, you are probably not measuring bilirubin. You are probably measuring just some simple colored species. So how do you actually use Beer's law in the lab? We're going to go through this step by step. So your step 1 is going to be determine the best wavelength to measure the absorbance of whatever you're measuring. So you are going to vary wavelength, and you're going to see how the absorbance changes, again, for your particular compound. And your graph will give probably kind of a funky shape like this with a couple different peaks. You want to choose your maximum. So the maximum for this compound, whatever it is 510 nanometers. So after you have chosen your wavelength, your step 2 is to create a set of solutions of known concentration. Now, very often this is done with what's called a serial dilution. So you're going to take a stock solution and you are just going to dilute it once, and then you're going to dilute it again and again and again. For this particular lab, I chose 5 knowns. So I know the concentration of each of these solutions. Now, ideally, for choosing what concentrations you want, you need to have some idea of your range for your unknown. Otherwise, you might be running this more than once. So you can see I've chosen my concentrations in the 10 to the negative 3 range. Again, this is molarity. But if my concentration ends up being much higher than that, like maybe my concentration is actually going to be 2.5 times 10 to the second, then I would not have chosen my knowns very well, and I would have to redo this. So again, ideally, you want your unknown to lie somewhere in the middle of all of your concentrations of your knowns. And if you're doing this in a general chemistry lab, either in high school or college, your instructor will give you the proper range to determine your unknown. Okay, so let's move on to step 3 here. You're going to create a calibration curve. So you have your set of known solutions. You are going to measure them at the wavelength that you have chosen. So you are going to put your sample in the cuvette and you're going to see what the absorbance is. So in this plot here, you can see I am plotting absorbance and concentration. So again, my concentrations are known. These are my independent variable. And it gives me absorbance, and I get a fairly linear plot here. And you can see, again, I'm pretty much going through the origin. This is a good thing because Beer's law, if you followed it perfectly, which you can't in lab, would give a y-intercept of 0. So now I have 5 points on a line. I need to perform a linear regression. So this is step 4. So I'm going to perform a linear regression on my data. Of course, there are multiple ways to do this. Excel is a great tool for this, but often calculators will do this as well. And you want to get an equation of a line. So for my data here, when I did a linear regression, this is my equation of my line. And you can see my y-intercept is really close to 0. Okay, great. Now I have an equation. What do I do with it? Okay, so this is step 5. So your step 5, you're going to measure your absorbance of your unknown now. So before you've been measuring absorbances of all of your known solutions. Now you're going to measure your unknown. So I take my unknown. Again, I put it in the spectrophotometer at the correct wavelength, and I get a value for the absorbance here. So my unknown has an absorbance value of 0.297. Now this is good because you can see my absorbance here is in between all of my standards. So I'm hitting about right in between all of my knowns. So if I'm going to put an X on my line at about 0.297 or about 0.23, I'm going to hit like right about here-ish. But if my unknown was hitting way out here, I would need to redo my calibration curve because I would need to choose better concentrations for my known. Again, I just want my unknown to lie somewhere in the middle of all of my knowns. They all need to be together. All right, so again, this is great. I can even see from the graph about what my concentration is going to be. So it's going to be somewhere in between 2 times 10 to the negative third and 3 times 10 to the negative third. So I get an idea of mathematically what I should get for my answer. Let's actually plug it in to our equation of the line and get an exact answer. So you know your absorbance. Absorbance is measured on the Y scale here. That means you're going to put your absorbance into your Y value here, and you're going to calculate X. Again, you're trying to find concentration. So here is my equation. You can see I plugged in my absorbance right here. I'm going to solve for X, and that's going to give me my concentration. So this is just a really simple algebra problem. I solve for X, and I get X is 2.37 times 10 to the negative third, which again makes sense kind of where I thought my range would be for my unknown, just looking at the graph and eyeballing it. So my concentration of my unknown is 2.37 times 10 to the negative third. Because my concentration of my knowns and on my graph is in molarity, this concentration also is in molarity. As always, we're just keeping units really, really consistent here. And that is how you perform a Beer's Law lab. I hope you found this video helpful, and thanks so much for watching.